Okay, let's talk now about permeability, or the ways in which materials respond to magnetic fields. All right, and I want to do this by contrasting it to electric permittivity. All right, so with electric permittivity, we have the idea that we have a material and we're applying an electric field onto that material, or embedding it in an electric field, if you will. And inside that material, we are going to have the molecules rearrange in a way that makes positive sides tend to go to the right and negative sides will go to the left, or the positives will basically be pushed in the direction of the electric field. In a material where we have, an untold number of molecules, it's not that every molecule aligns nicely like this clean picture shows, but you may have a slight imbalance. You might have 51% pointed in one direction and 49 pointed the other. It's really an arbitrary distribution. But that little tilt is enough to make a difference. And the stronger that electric field gets, the bigger that tilt, or the bigger that imbalance between those aligned to the right and those aligned to the right, to the left, are going to be. And we define a vector P that we call the polarization vector that loosely describes to what extent we are separating charge by aligning the molecules, overall in one direction. And this vector P had units of Coulomb meters per meter cubed. Right? Coulomb meters is a charge moment. It's how much charge we are pulling how far apart. It's a measure of how much we're separating charge, and then divided by meter cubed is a density. It's per volume. So this worked out to be coulombs per meter squared. And from that, we figured out that the relationship between D and E can be written as follows: D equals epsilon naught E plus P. We then approximated that P will equal to epsilon naught times some susceptibility times the electric field. For many materials, it will be true that there's going to be a sort of a constant proportionality constant between the strength of the electric field and the intensity of the polarization. So this enabled us to rewrite D as D equals epsilon E, or epsilon equals some relative value times the free space value, and the relative value equals 1 plus this proportionality constant chi. All right, so let's try to analogize this for the magnetic fields. All right, so here's a material, and we're going to envision applying a magnetic field H, which I'm going to draw it coming out of the page. And we've embedded this material in the magnetic field, like this. Right, so there's the magnetic field. Now, what will happen to a material is that molecules also have a tendency to spin around. And as they spin around, they can create really, really small currents via those molecules. Right? So the molecules are basically going to start to rotate in the presence of this magnetic field. Right? Because you can almost look at it as if the molecules themselves have the ability to make a small current. Right, so this spinning of the atoms in response, instead of a P, we're going to have a vector called M. M is a magnetic polarization, right? It's the degree to which we have lots of spinning circles or lots of current. And all those little currents are creating their own magnetic field as well. Right, now M has units of amps meter squared per meter cubed. Amp meter squared is basically a measure of how much current we're making. And then if you make current go in a circle, right, you can either have more current to intensify that, or you can have that circle be bigger and bigger, in which case the source of that basically scales with the area of that circle as you make it bigger. So we need an amps and we need a meter squared to represent that area. And that's sort of a measure of current sourciness. and the divided by meter cubed is because we want a volume density of that. So that works out to be amps per meter for this magnetic polarization M. All right, so this is magnetic moment per unit volume. Now the equivalent of this P equals epsilon chi E in the magnetic field sense will be the following. It's going to be that M for lots of simple material will equal to chi M, a magnetic susceptibility, times the magnetic field H. All right. This is very similar, except here we had an epsilon naught and here we don't. But other than that, it's a nice parallel. And if we substitute all that in, we end up with B equals mu naught H plus mu naught times M. And if we substitute our relationship here, M to H, then we get B equals mu times H, where mu equals mu R times mu naught. Mu R equals 1 plus this magnetic proportionality constant, and mu naught equals 4 pi times 10 to the minus 7 henries per meter. Let's compare that, by the way, to epsilon naught, the permittivity of free space, which was 8.85 times 10 to the minus 12 farads per meter. You can see a little more of the duality there, and then epsilon had units of farads per meter. Farads is capacitance. For the magnetic fields, mu naught was defined with henries per meter, inductance. And henries and farads, or inductors and capacitors, are basically analogous to each other, except one's on the electric side and one's on the magnetic side. All right, so this kind of makes sense overall. All right, now let me just talk a little bit about different kinds of materials. There are basically two ways in which a material can respond, and those are called paramagnetic and diamagnetic. For electric fields, as you may remember, we had this idea that for most materials that we're going to cover in this class, we had this idea that epsilon R will always be greater than or maybe equal to 1. Right, that you can have a higher permittivity, but you can never have a smaller permittivity. There's a class of wacky materials for which you can have epsilon R is less than 1. We're not going to cover that in this course. Let's just say they're weird. For magnetic fields, though, there's a little more flexibility in that there are sort of standard, regular, off-the-shelf materials for which this magnetic susceptibility is greater than 1, and others for which it's less than 1. A chi of greater than 1, sorry, this should be a chi M right there. For chi M of greater than 1, that implies that, epsilon, that implies that mu R is greater than 1. And if the magnetic susceptibility is less than 0, that implies that mu R is less than 1. Right? And so paramagnetic materials are the ones for which the magnetic susceptibility is greater than 1. Here's some examples: tungsten, cesium, aluminum, lithium, magnesium, and sodium. And the sort of diamagnetic materials are ones for which you actually have a negative response to an applied magnetic field. And here are some examples of that. All right. In addition, there are also a small number of materials called ferromagnetic, for which mu R is much greater than 1. And these are what we know of as magnetic fields, as magnetic materials colloquially, right? So these are things that are attracted to magnets, things like cobalt, nickel, iron, or permalloy. These have very high values of relative permeability. As high as, I think in the case of iron, it's about 280,000. So it's pretty ridiculous. And this is what we call magnetic materials, colloquially. So this is what would stick to a magnet, to a permanent magnet. All right, so that covers paramagnetism and diamagnetism, or the way materials respond to magnetic fields. And that concludes section 3 on permeability. In the last portion, now that we have talked about magnetic materials, we want to talk about how magnetic fields are going to change on the boundary of two materials. And it's going to depend primarily on the permeability of the materials on both sides of the boundary.